Hello, in this example, we're going to do another trig substitution problem. Remember, for trig substitution, there's three big parts like we've seen before. The first part is, well, once we convinced ourselves we need to use trig substitution, which is typically indicative that we see things like x squareds under square roots and things like that, and a u substitution won't just help us out. So in this case, we have that square root of 1 minus x squared. If we try to think about what u substitution might work, or is this an integration by parts, it's not really clear that either of those will be very fruitful. So we're thinking, let's use trig sub to help us get rid of that square root. So once we've convinced ourselves this is a trig sub problem, there's three steps to it. The first thing, introduce trig through the appropriate substitution to help us get rid of that square root term. But once we've introduced trig, we're going to be left with a trig integral, or an integral fully in terms of trig functions, that will compute using trig identities or other types of ideas that we get. And the third thing, once we have our antiderivative from that trig integral, it'll be in terms of the trig variable theta. We need to convert back to the original variable, like you can see in this case, which is an x. So for this integral, we're going to use trig sub to compute it. And for trig sub, like I said a moment ago, the first thing for us to do is figure out, well, what is the appropriate substitution for us to make? And remember, the way that we introduce trig into these integrals is typically through trying to build towards one of these Pythagorean identities. So at the end of the day, somewhere along the lines, we have a square root of a trig function squared, and that'll just help us get rid of the square root. All right, so when we're trying to identify which identity to use, we're really trying to see, well, what do we have underneath the square root? In this case, we have a 1 minus x squared. So if we're comparing that to the identities that we have, well, the identities we have are cosine squared, 1 minus sine squared, secant squared, 1 plus tangent squared, and tangent squared is secant squared minus 1. And well, the second identity on the right-hand side doesn't have any minus signs. So it looks like that identity's out. So that minus sign being there really helped us get rid of one identity so far. The next thing for us to kind of figure out is, well, underneath the square root, where is the x term? The x term is after that minus sign. So we have a 1 or some number minus our variable squared. So when we're comparing that to the right-hand side of our trig identities, we can see, well, which one of these identities has a 1 minus something squared, or 1 minus our trig function squared. And in this case, it looks like the identity that's going to help us out is that first one, the 1 minus sine squared, because again, our square root has a 1 minus x squared, or 1 minus our variable squared. So I'll just cross out the third identity. So in this case, again, we're trying to build under that square root something that looks like the right-hand side of that identity. So if we're trying to do that, it looks like our substitution we're going to be making is going to be related to sine. So I'm just going to pick apart our square root. So again, putting the integral aside for a moment and see what's underneath that square root. Now we know we want to make a sine type substitution. The other thing we need to recognize is, well, if I put a sine under that square root, are there any basically numbers that aren't going to look exactly like that right-hand side of our identity? And in this example, well, we have a 1 sitting there. We have a 1 coefficient really in front of the x squared. So it looks like if we just let x equal sine in this case, we'll get that identity under the square root. So we're going to move forward with x is equal to sine of theta. All right, so let's start substituting that into our integral. So anywhere there's an x, we can substitute in a sine of theta. So under that square root, we have a 1 minus what we plug in for our substitution. We're going to square that. And then also in that denominator, we have an x squared. So we can write that as our substitution we're making, that sine quantity squared. And now, of course, we plugged in all the x's for our new thing, which is sine of theta. But we still need to figure out what our dx is in terms of our new integration variable, which is going to be a theta. And similar to a u substitution, we differentiate to get that relationship. So if we differentiate x with respect to theta, that is differentiating sine with respect to theta gives us cosine. And then again, we're trying to solve for that dx in terms of d theta. So if we multiply both sides by d theta, we will get that dx is equal to cosine theta times d theta. So we can plug that in down in our integral. And again, that was our dx originally. All right, at this junction, we just have a little bit of algebraic massaging to do for this integral, basically to help us see what's there. Also to make sure we're getting rid of the square root. So under that square root, we have a 1 minus sine squared after we square what's in parentheses. Down below, we have a sine squared. And we're still multiplying by that cosine d theta. So whole purpose of this trig substitution is to help us get rid of that square root. In this case, again, going back to our substitution up above or our identity up above, we know that cosine squared of theta is equal to 1 minus sine squared of theta. So under that square root, we have a 1 minus sine squared. We can replace that with a cosine squared. And we divide by sine squared of theta, and then multiply by cosine theta d theta. And this is where the trig sub kind of substitution actually help us out, because again, we have the square root of cosine squared. That'll just result in a cosine for us. So then just collecting the terms, what this really looks like for our trig integral is we now have a trig integral of cosine squared all over sine squared d theta. And again, at this junction, we've introduced the substitution, or we've introduced trig into that integral. We now have an integral fully in terms of trig, and this basically ends Act 1 of these trig subproblems. We've gotten the trig integral. Brings us to part 2. Compute that trig integral. And in this case, if we look at what we have here, there's a couple different ways we could try approaching this integral. We have a cosine squared over a sine squared, which we could rewrite as a cotangent squared. So one reason we could rewrite as a cotangent squared, let's see what happens. Now the tricky thing with this is, I don't know a function whose derivative is just cotangent squared. So at this junction, we could hope for an identity to help us out. And it turns out, well, if you know some other Pythagorean identities, cotangent squared is actually equal to cosecant squared minus 1. So if you know this identity, we could make that identity, or we could substitute that identity into our integral. So if we substitute that identity into the integral, we get, well, this is now the integral of cosecant squared minus 1. And why we might want to do that is, well, if we look at each of these terms, we can anti-differentiate a constant. We can also anti-differentiate this cosecant squared, because we know that, well, negative cotangent's derivative is a cosecant squared. So if we went this route of turning cosine squared over sine squared at the beginning into a cotangent squared, and we knew this Pythagorean identity, we could get an integral that we could anti-differentiate. So this thing would be equal to a minus cotangent of theta minus theta plus c. So that's one way we could have done this integral. I'm going to do this another way just to show you we do play around with these trig integrals a lot of times in the middle of trig subproblems. That being said, if you find the antiderivative, you're fine, move on to step 3. For this, I'm really just kind of showing us that there sometimes are multiple different ways that we could approach these trig integral problems, these trig integrals inside of these trig subproblems. So for case number 2, say we didn't want to make this a cotangent squared. So we didn't make this a cotangent squared right from the start. So again, we're starting off with the integral of cosine squared over sine squared. One thing we could try to do is rewrite a sine squared or a cosine squared into the other trig function. So in this case, if we try something like, say we use another Pythagorean identity, cosine squared is 1 minus sine squared of theta. We can substitute that in for that cosine squared in the numerator. And what that'll help us do is, well, we'll see in a moment. We have 1 minus sine squared sitting upstairs in that numerator. Downstairs, we still have the sine squared. But more importantly, at this junction, what we recognize is by doing that substitution in the numerator, we still have one thing in that denominator. So if we wanted to, since we're adding or subtracting things in the numerator, dividing by only one thing, we could break that up into 2 separate terms. So we could rewrite this as 1 over sine squared of theta minus a sine squared over sine squared of theta. And if we rewrite this in terms of trig functions we know, a 1 over sine squared, hey, that's a cosecant squared of theta. And a sine squared over sine squared is a 1. So we have a minus 1 d theta. And this might look a little familiar from before. If we take a look at the integral we just got, it's the same integral that we arrived at before by doing that cotangent squared substitution at the beginning. So this, of course, still has the same antiderivative, minus cotangent of theta minus theta plus c. So we're able to do this particular trig integral a couple different ways, just to say that we can play around with some of these substitutions and see what works, what doesn't work. But either way, at this junction, we have we have an antiderivative that we need to go from the theta variable back into the original x variable. And that brings us to step 3, or act 3. Convert back from theta into x. And again, to reiterate, when we did this type of thing for a u substitution, this was almost a no-brainer step. We could just go back to the substitution, plug in what we have for u, and we have our antiderivative in terms of the original integral, or the original variable. In this case, if you remember all the way back, our substitution was x is equal to sine of theta. So this was the substitution that we made at the very beginning. If we look at what we have here, which is sine theta stuff that can relate it back to x for us, inside of our antiderivative, we have cotangent stuff. And well, we also have this single theta that's sitting there that we'll handle in a little bit. But all this to say, we can't just directly resubstitute our substitution into the antiderivative like we could for u substitution. So like we've done in previous problems, we've taken our substitution that we made, in this case, x is sine theta, and we've solved it for that trig function. So we can write this as sine of theta is equal to x. Or since we're going to try and put this in terms of right triangle stuff, we could make this equal to, well, x over 1, since anything over 1 is still the same thing. And remember, at this junction, we try to think about, okay, I have a sine sitting there. What is sine in terms of opposite, adjacent, hypotenuse stuff? And if you remember back to your trig days, sine is equal to opposite over hypotenuse. So we're going to draw a right triangle in a moment. and fill in the sides. And since we're thinking about the sine of our angle theta, looking at what the opposite side is of the triangle, again, that's the side opposite of our angle, that's just going to be what's in that numerator of the ratio to the left, x. Now, if we do a similar thing, the hypotenuse side of our right triangle is always the longest side. And in this case, that's just going to be what's in the denominator of x over 1. So the hypotenuse side's length is 1 in this case. And just like we've done in previous examples, well, we still have that third side to find, and we can use the Pythagorean theorem to help us find it. Now, because we're looking for one of the side lengths that's shorter than the hypotenuse side, we use basically, instead of a squared plus b squared equals c squared, we have the side length is equal to the hypotenuse squared minus the other side we know squared, all under a square root. So this third side is equal to 1 squared, which is 1, minus the opposite side squared, which is x squared. And again, that's coming from Pythagorean theorem. All right, so this is what we've done in previous problems for our antiderivative. So if we look back at our antiderivative, we do have a trig function there, the cotangent. So we can try to figure out what that cotangent is. Cotangent of theta is equal to, we can grab the appropriate sides off of that triangle. A cotangent, again, is equal to 1 over tangent. Tangent is equal to sine over cosine. So cotangent is a cosine over sine. And if we go through all the opposite, adjacent, hypotenuse stuff, we'll see that cotangent is adjacent over opposite. So if we're grabbing those values off of the triangle, the opposite side is x, so we can put that on the bottom. And the adjacent side is, well, that's the side that we got from Pythagorean theorem, 1 minus x squared. So in terms of our antiderivative up above, we can get that cotangent term once we have that right triangle. The piece that we still need to figure out, though, is, well, we have that single theta there. What do we do for that single theta? And, well, we can't just grab that value of theta from the right triangle as we have it set up. So what we do is actually revisit our trig substitution. So I'll just make this little note for the single theta. Basically, what we're going to do is introduce, or use, I should say, inverse trig functions. So we're going to start back with what we have from our substitution, which is, we know that, well, sine is equal to x over 1. Sine of theta specifically. And again, what we're trying to do here is solve for this theta value by itself. And the way in which we can do this is, well, to get that theta value by itself from inside of that sine, we want to take the inverse sine, or the arc sine, of both sides of this equation. Remember, we have an equation, so left-hand side equals right-hand side. What we do to the left, we do to the right, and we maintain that equality. So if we take the inverse sine of both sides of this equation, we'll get the following. I guess I could just write, instead of x over 1, just, well, x. Left-hand side, we have the arc sine of our sine of the angle we want. Now, the right-hand side is just equal to whatever the inverse sine, or the arc sine, of x is. That left-hand side, though, if we take the inverse sine of sine itself, we just get back what's inside of that sine argument. In this case, that theta value that we actually want. So inverse sine of sine just gives us that theta back. So we find that in this problem, theta by itself is arc sine, or inverse sine of x. So we have everything we need now to basically plug in what we need into our antiderivative that we found. So the antiderivative, again, was minus cotangent of theta minus theta itself plus c. So if we just plug in what we found for cotangent from our triangle, this again is minus the quantity from the triangle, the square root of 1 minus x squared, all sitting on top of just x. And then for the angle itself, we found that that's minus, well, the arc sine of x, or inverse sine of x. And then finally, plus c. So again, just to reiterate, where that inverse sine is coming from is from finding that single theta by itself that we need for the antiderivative. That other piece we got was coming from cotangent itself that we got from the triangle. But either way, this is our antiderivative in this problem. So again, the new thing in this trig sub problem that we didn't see in the previous examples is what do we do when the antiderivative we have has a single theta sitting there? We introduce the inverse trig functions to help us get that theta value in terms of x.